think I got it. All right. Last time we had discussed motion diagrams, and we did that for a few reasons. And then the main purpose is to describe motion. And we also did the motion diagrams so that we can better visualize how accelerations are going to look. So that's the purpose of that. What we are aiming to do now is those very qualitative descriptions of motion, and we want to start to throw some numbers behind things. We want to make this more mathematical now. And so the way we're going to do that is we're going to start to develop what we call position time graphs. So in this picture here, we have a motion diagram of somebody walking to school in a straight line, apparently. And we have a coordinate system placed down to help us put some numbers behind things. And each delta t apparently is a minute in this picture here. And we can see what the motion is, so we can easily describe this. This person moves at a medium pace and for about 3 minutes. Probably something catches the student's attention for another 3 minutes, and they slow down quite a bit. And then for the subsequent 3 minutes, they probably are freaking out that they're late to class, so then they're running. So that might be what the motion looks like. And what we can do with this is when we want to transition this into a position versus time graph, then what we do is we create time on the horizontal axis and position on the vertical axis. Okay, notice that the axes are labeled with the appropriate units for what we're doing. And every point that we have in our motion diagram, can be placed as a point on the graph here. Okay, placed as a point on the graph. So now we have these. It's too difficult with that on. All right, so now we have here, points separated by intervals of time. And what we do is we can simply connect the dots with straight lines, and then we have our position versus time graph. Now, assuming that this was true uniform motion, right? This is the approximation or sort of averages of how this person moved. And there's a lot of information here. These lines are straight, which means a constant speed. The slope of the lines, right? That would be in units of meters per minute, which is a way to measure speed. We would do meters per second, but the slopes of these lines are telling us information about how fast things are moving. There's little kinks in the graph. Those are, you'd consider these like discontinuities here. These are not, it's not a smooth transition, but it's okay because this is still a description of the motion. We're putting a little bit more math behind it, but we're not being super strict about the math right now. Okay. So I have a lot of questions for you today. So in the chat, go ahead and put what position versus time graph you think works with this motion diagram. You want to pay attention to whether position is positive or negative. You want to pay attention to whether velocity is positive or negative, and then see how that's represented on the graph. Okay, a lot of C's, a few D's. Okay, well, I'm guessing it's C. Y'all think it's C? It's C. Why? Well, let's look at the other ones and determine why they're wrong. That's a good thing to do. Number A. A is showing our position increasing in time. That's not true, right? We're going to the left. This is saying we're going to the right. Wrong. B is saying the same thing. It's saying we're increasing our position and moving to the right. The only difference between A and B is that B starts at the origin. Well, that's still false. What's wrong with D? D says we start at the origin and move to the left, which we don't, right? C is correct. We start off with a positive position that's steadily decreasing. At some point, we do cross the origin, and we continue to move to the left. Notice the slope of this line. It's a negative slope. It's a linear line, but it's a negative slope. And the slope of this position time graph is what the speed is. Or I should say formally what the velocity is, because the fact that this is negative does tell us that we're moving to the left. Okay, good.
Professor, I actually have a quick question. So the starting position for C would be on the origin?
No, the starting position for C is somewhere to the right of the origin, apparently. Whereas D has it on the origin. Yeah. So a way to think about this is, see this axis here, that's kind of been flipped on its side here. It's now the vertical axis. But you're looking at the behavior here. The position's positive. It continues to decrease. It crosses 0. And then it moves more to the left. So.
Okay. Yep. Thank you.
Mm-hmm. So let's do something. Let's construct one of these things, actually. We had a story here. Age-old story of Bob and his lamppost at home. All right, so let's see what we got here. Bob leaves home at 9:05, runs at a constant speed to the lamppost, reaches the lamppost at 9:07, immediately turns and runs to the tree. Bob arrives at the tree at 9:10. We want to draw a position time graph and find the average velocity. Okay, so we start at home. So first thing you do, of course, when you draw these is you have to make sure that you have your coordinate system. So that's what we have here. Oops. Back a little bit. This does not come up as clearly as I would like. All right. I wonder what's going on here. It's a little... Try to zoom in a little less. Less, I can see more. That's not how zoom's supposed to work, though. When I say zoom, I mean not zoom. Adobe is having some issues. All right, I'm gonna zoom out. Okay, I guess we're doing like this. Okay, on the horizontal axis, right, is my time, and I have it in units of minutes. So I indicated minutes over there, and I go from 1 to 5. That's good. My vertical axis, I'm using yards here now. It's not SI, but we're just looking for a description of motion here. I can stick with yards. It's perfectly fine to do that. I'm not doing any kind of crazy calculations here. But I'm going to draw the full extent of this area. So from 0 up to 1200 is going to be the yards for this. And what we do is we're going from home to the lamppost in 2 minutes. So I draw a point at t equals 0 and x equals 600, and another point down here at t equals 2, and the x is going to be 200 here. And assuming that Bob is a steady jogger, right? Constant speed. This line represents that person's motion, and then we turn around, or Bob does, and goes towards the tree. So we draw another point for the tree, draw a line from that, and then we sit back and we admire the great work that we've done. And we see that the first one is a negative slope, meaning we move to the left. The slope of that line is negative 200 yards. I put in my, my rise over run, rise over run. And that comes out to negative 200 yards per minute. The other one looks steeper, so I put in my rise over run for the slope here. We get 330 yards per minute. So great. So that's the average velocity for these two parts of the run. It's a real basic example here, but that's how we're able to form this graph. Is there any questions about this?
Professor, can I ask why the slope is negative at the beginning?
Yes, the slope is negative because we're moving to the left, and the left is what we've called negative.
Thank you.
Yeah. So that's one thing that's very important to recognize about at least these graphs. The slopes tell you two things. The steepness of the slope tells you speed, and the slope is either going to be negative or positive, and that tells you direction. Because if your velocity is negative, that's about direction. Right? All right. Let's keep going. Any other questions, though, before I move on from here? Okay. Let's go back to here. Okay. Here's another, well, here's a position versus time graph. And we want to describe what the car's doing in this situation. So we want to come up with a story, basically. So we're kind of going backwards. All right. So well, what's happening here? It looks like we are starting 10 kilometers away from whatever we're calling the origin. I don't know where that is. You know, this whole graph is sort of divorced from a scenario, so we can just come up with one. We move to the left, or we move towards the negative positions, whichever way that is. We eventually cross the origin after 10 minutes. And we travel for an additional, looks like another 20 minutes. The whole trip, that whole first part of the trip was 30 minutes long. And if it's 30 minutes long and we traveled 30 kilometers, we're traveling a kilometer per minute now. It is negative. What happens is we abruptly stop when we're 20 kilometers to the left. We just abruptly stop. We have like an infinite acceleration, basically. Just stop. And then we relax for about 10 minutes. 10 minutes? Yeah, 10 minutes. We're just relaxing. This is probably a drug deal, to be honest. But anyway, okay, so the drug deal takes 10 minutes. Okay, you parked in the parking lot, you're waiting for your shrooms, the guy comes, you get your shroom. I'm just joking. That's not how you get that stuff, of course. Then for the next 40 minutes, we're going back to the origin. And that's a little slower, right? Because that slope's not so steep. It's half as fast, actually, right? 20 kilometers over 40 minutes. That's half the speed. It's a half kilometer per minute. And that's what this car did. So we have three different types of motion here. We have moving to the left. We rested for 10 minutes. We moved to the right for a little while. We have some abrupt stops here. We have some abrupt changes in motion. These little corners here, there's probably detail there about exactly what occurred, but it's not relevant for the overall behavior of what we're trying to describe. So we're just it's not a detail that we are interested in, unless it becomes something we are interested in, and then we have to incorporate that. But, one thing that's a little frustrating with physics is to understand the level of simplification or assumptions you need to make in problems. And that's not a simple thing to navigate. Sometimes we have to make problems a lot simpler than they seem like we need to. Sometimes we have to incorporate harder things and are necessary to incorporate. So it's something that you just sort of learn with experience. So that's all I can really say about that. But, for a problem like this, do we care about exactly how we hit the brakes and came to a stop? Probably not. Probably not. So, all right. Question for you here. This is a position versus time graph. At 1.5 seconds, what is the object's velocity? At 1.5 seconds. Letter in the chat. Letter in the chat. Oh, by the way, as you are putting your letters in the chat, the homework that you turned in on Tuesday, I put up the solution to that today. I didn't do it Tuesday because I was occupied. Okay, let's see what we got here. What is it? Let's see. Okay. Uh-oh. No, the house did not flood. I'm actually selling my house. Because I'm selling my house, there's just chaos happening. So, I'm in the midst of chaos. C? I don't know about C. I don't like C. I only think it's C, but you know what? I'm not so happy about C. Yeah, it's true, actually. We're going to leave. You know what? I'm going to do that. I don't care if it costs me $100. I'm leaving that ring there. I'll pass that on to somebody else. That's pretty funny, actually. C, come on. It can't be C. It's B. It's B. Well, how? Well, it's just the speed of the object, or the velocity, right, is determined from the slope. What are we doing here? 20 meters over 1 second? That's 20 meters per second, right? That's what we did here. Now, I know what you did. You crazy kids. This is what you did. You looked at 1.5 seconds. You went up. And you're like, oh, look, it's 10. The answer's 10. Well, that's position, though, right? Not velocity. Velocity is the rate at which your position is changing. When you have a position versus time graph, you need to be inspecting the slopes. Okay, so it is B. It is B. All right, knuckleheads. Next question, see if you get this one right now. What is the velocity at 3 seconds? What's the velocity at 3 seconds? All right, let's see it. D, people, D? Okay, D's right. I'm joking. D's right. You got it. I think a lot of you learned something just now. I think some of you just learned something because you got the first one wrong and you got the second one right, and I'm going to attribute that to learning. So congratulations on that. You calculated the slope at 3 seconds. Now, what was not important? Not incredibly important information in this problem. 3 seconds. In fact, I could have changed this question to be anything in the area of 2 to 4 seconds, right? Anything in 2 to 4 seconds would have this answer as D. There's nothing special about 3 seconds. There's nothing special about 1.5 seconds. By me saying 3 seconds, it's highlighting the area of the graph that you need to pay attention to. And we can see that at 3 seconds, we are involved in the motion that took place over 2 to 4 seconds. So if I said at t equals 3.5 seconds, what's the velocity? Y'all are going to say the same thing. Okay, great.
Can I ask a quick question about this?
Bet. Ask as many as you like.
Yeah, on this one I picked D because it was negative and it was going down. But I was kind of confused on why it wasn't 20 either. But like if it was a negative 20, that's what I would have possibly went for. But I was kind of having a hard time.
Well, it's because you're trying to calculate a slope of the line, right? So
yeah,
traditionally in math, you would do rise over run, right? So the top portion of the slope, right, is going to be 20 minus 0, or 0 minus 20, I guess you'd say. 0 minus 20 divided by 4 minus 2. So it's 20 meters over 2 seconds, basically. So that's the rate. And you can see the lines are different, right? This one's more steep. This one's less steep, and so on. So that's
okay.
Yeah. Somebody asked, what is the speed at 2 seconds? I don't know. We don't have enough information to tell. We turned around, and I would argue maybe instantaneously it's 0, but we don't have enough information to tell because we got this little corner in discontinuity here. So if we really want to know what's going on at 2 seconds, we are going to ask the person that gave us this graph, can you please elaborate on what happened at 2 seconds? And then we can consider it. So that's what's going on here. All right. This one is rad. This one is a pretty rad problem. How would you interpret this position time plot? All right, look what's going on here. We got seconds, we got minutes, we got a line going around here, and then all of a sudden it comes up, and then all of a sudden the line goes all the other way. So what the heck is happening there? Letter in the chat. Let me know what you think about that. I forgot option D. Option D is this person is a time bender. How about that? This person's a time bender. That's a possible option here. Actually, there's multiple options. This person could be a time bender, or this person has the ability to bilocate. Bilocation is an ability. So a lot of B's, a lot of C's here. Somebody had a question, I thought. Maybe they did not. There's so many people in this class. So many people in the class. How about this? If you get it wrong, if you get any future questions wrong, I'm just going to drop you. Because I can't, there's too many students in this class, too much. So as I'm going to weed you out. How about that? Oh, brother. Okay. All right. I won't do that, I guess. All right. It's okay. No. Answer questions. I'm joking. All right. It's C. It's not possible to do this. It's not possible in this universe. I'll put it that way. Now, how would you do this? What is this saying here? Well, position versus time graphs need to be one-to-one functions, right? They need to be one-to-one functions because what this graph is telling me is that something is located at two places at one instant in time. So at 4 seconds, we have something located at what looks to be 3 or 4 meters, but then we're also located up near 10 meters. So that's probably not a thing. I don't know. And then, or maybe this is, you know what this is? This actually could be like the Dragon Ball fusion. And then at 10 seconds, they fuse right there at 6 meters. Okay, this actually could work for Dragon Ball fusion, I suppose. But for most normal people, you can't do this. Okay, you can't go backwards like this. Because it either implies bilocation, it implies going backwards in time. So, yeah, okay. So, anyway, the entire point of this slide is one-to-one functions. That's it, one-to-one functions. Okay. Oh,
So
yes.
it doesn't work because it's going backwards.
Well, it's not really clear what it means. It's not going backwards though, right? Because this line is going backwards in time. Like, it just doesn't make any sense. It's just, I don't know how you would interpret this properly. Actually, if it's a single object, then I guess you could say you're going backwards in time, which unfortunately we don't cover time travel at least in physics 110. So.
Okay. And what is
so these are one-to-one graphs. These only progress forward. That's it.
And what does it mean by uniform speed? Like
constant speed. It's another constant speed. Yeah.
Okay.
Constant speed. We use the word uniform more than I use the word constant. It's a nice. I don't know why. All right. Now I'm not going to answer this question here, but I'm going to go through it with you, right? So what we have here is we have a little coordinate system established with Q, R, and P represent different positions down here. And we have a story up here. And we want to match the story with the proper position time graph. I love these questions because I like to eliminate answers. That's the fun part, is trying to figure out why everything's wrong, right? A person initially at point P in the illustration, all right, so we're here. We move along the axis to Q. So we go to the left. We move to Q. And stay there for a moment. Then we run quickly to R. Stay there for a moment. Then we go back to P. So it looks like we spend the entirety of our time in between Q and P. We just kind of go back and forth. So let's figure out what's wrong. Okay, immediately I can eliminate option 1. Let me do it. Let me do it right now with a big nasty red X. This is wrong. Actually, that's too cluttered. I can't read that. Okay, number 1's wrong. Delete. Okay, I won't go crazy with the stamps. Number 1's wrong. No, red. Zoom. Wrong. 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 Automatically wrong. Somebody tell me why. Why could I eliminate those immediately?
Because you're not starting at 1.
There's a more obvious reason though why I'm picking 1, 3. They go under 0. Joaquin, the hero of the day. 1, 3, and 5 show positions that are negative. We never cross the origin in our story. So those are automatically incorrect. Now, I forgot who spoke up there, but whoever you spoke up, your explanation is correct for allow eliminating number 6. And number 6 is wrong because it says we start at the origin, and we don't start at the origin. So now we're left with 4 and 2. And now we got to look at those two, and they look so similar to each other, but there's some slightly different behavior going on. Looks like we start at the same place, but notice the very first part here of 4. When we go down in position, that's quite steep. It's a pretty steep thing. That's indicating we're moving very quickly. When we go to 2, that's a little shallower. So that should be a difference. And then back to 4, we rest for a while, and then we got a very shallow slope here, and at number 2 we got a very steep slope. Okay, so there's some big differences there. Let's go back to our story and figure out what's happening here. We move along the axis to Q. That sounds like a casual thing that we did there, right? That should be kind of moderate in speed. Then we run quickly to R. It's 2. It's 2. Sorry, 4. Nobody likes you. 2 is correct because it does match with the different speeds. Look at the first slope here. It's kind of, looks like a 45-degree slope there. Not that that means anything, but the second part of the motion is faster, and we can see the last part of the motion is much slower. And this is all based on the steepness of the slopes, right? We're all based entirely on the steepness of the slopes. There's no numbers here, just the qualitative behavior of the slopes. So 2 is the right answer. Okay, that was a great problem. Any questions about what we did there?
So just based on the steepness of the slope, we were able to say that 4 is wrong and 2 is right?
Yes.
Okay.
Because 4, if I told the story of 4, here's what I'd say. We very quickly run to Q. We very slowly stroll back to R, and then we really quickly go back to P. That doesn't match up with the story.
Okay.
It says that we sort of moderately walk to Q, very fast to R, and then we casually kind of stroll to P. So
Got it.
that's how we're seeing these slopes. The slopes just look a little different.
Got it.
Yeah.
Thank you.
Okay. Anything else? Okay, let's keep chugging through it. What time we got? I have no idea what the time is. That clock, it says it's 9:30. Well, it's not 9:30. It's 11:35. Okay, clock. You were right a little while ago, but not now. All right, I gotta erase this stuff. I wonder how many X's I can put on the screen until it crashes. Zoom.
You can do a lot. I've tested it before.
Yeah. All right. Well, maybe during lab, I got some time. I got an hour and a half. I'm not helping people. Let me try it out there. I don't got a lot to do during quarantine, Got to figure out activities. Okay. This person with a giant grin, this person's loving their bike ride right now. Ooh, it sounds good, like a good idea too. But the idea of uniform motion, right? The idea of uniform motion is for when we're talking about our motion diagrams and things like that, equal intervals of position for equal intervals of time. Okay. Now, the way you see it displayed here, we would describe this as being an average, though, because if this person's on a bike, right, and they're, pedaling along and it says they're going, 25 miles an hour, if you would say, I'm going at a constant speed of 25 miles an hour, but then if you really start to change the time interval, What if it's not per second, right? What if it's not per minute? What if it's down to like 1/10 of a second? Is that truly uniform motion when there's little hiccups when you pedal and things like that? We make the assumption that it is, basically uniform. We don't care about the little hiccups that's going to happen when you go over rocks or even if you have to slow down a little bit to get out of the way of, an obstacle or something like that. It's that those details may not be very important. So when we look at our position versus time graph, what we're doing is we're seeing equal displacements for equal intervals of time. And so we call this the average velocity. Okay. And this is how it's defined. That triple line there, you'll see that a lot. If you don't know what that is, it means definition. The definition of average velocity as a magnitude is the rate of change of position over time. Okay. They say X and Y, that's not important. It's just position. Position. Doesn't matter if it's X, Y, Z, Q, P, doesn't matter what it is. It's position, right? But then, oops. So what we can do then with this kind of motion here is we can develop an equation, right? This is a linear line. And so from that we can develop an equation. Now the speed is the slope of the line. So that represents the mx. Like if you're thinking about this as y equals mx plus b for like a linear line, right? You have your intercept here, right? And you have your speed and time. So that represents the slope there. And time is the variable here. And this tells us what some future position is. So this is very straightforward. This is just a linear thing. And this is honestly our first equation. It's a very simple equation, and it only applies if you have no acceleration. You have a constant speed. Okay. Now, also notice that we use the letter S. You will see that a lot. S is intended to be a generic direction. When we want to avoid confusion, I don't want to show you an equation and it has an X in it, and you think, oh, well, that only works for the X position. Y position has totally different equations. It does not. So S is meant to refer to some generic direction. It could be up, down, left, right, whatever. But the one thing that does matter, it is one-dimensional motion now. We're only dealing with one-dimensional motion at the moment. All right, now, the idea of average velocity is fine, but I did mention this thing about, well, what if we looked at smaller intervals of time? Like, what is truly uniform motion? And the idea of this gets to this other concept that we call instantaneous velocity. So the difference being the average velocity are deltas, delta S over delta T. Whereas the instantaneous velocity is exactly what it sounds like. What is the velocity at a single instant of time? And the way we would form that is we take that definition of average velocity, delta S over delta T, and we take the limit that delta T goes to 0. So when we are sampling our motion, we're not choosing 1 minute, 1 second. We're saying this, that if I were to choose 1 minute, the answer is the same. If I choose 1 second as my interval, the answer is the same. If I choose 1/10 of a second, the speed, the answer is the same. So the idea behind this is that this limit turns this ratio into a derivative, dSdt. So it's the derivative of position, which yields the velocity. And that is the relationship between the two things. So here's a good illustration of what I was talking about here. Now you can see here, this motion, this is not uniform, right? They say this is some accelerating rocket. Okay, great, whatever. We have a motion diagram on the left here. We have a position time graph here showing that we are increasing position more and more as we go forward in time. So to be clear, this is not uniform motion. We are accelerating here. But you can see the problem with our definition of average velocity, because how do you characterize the speed? Because the speed is constantly changing. So what you do is you still consider, okay, I'm still going to make a slope. So I'm going to choose a delta S over delta t, but you let the delta t's get smaller and smaller and smaller and smaller. And so in this graph here, we're now sampling, finer points. And if we're zoom in here, it's like, imagine zooming in a lot. If we zoom in a lot, this curvature doesn't look so much like a curve now. And then our average sort of approaches a value, right? There's sort of basically a slope here. When we zoom in on that curvature, it looks more and more straight, and that means it's approaching a value. And that is exactly what a derivative is. Well, I think B is parabolic. It's not exponential. That's a parabolic curve. So constant acceleration always parabolas. And the derivative of a parabola is a linear line, right? So that's the relationship here. Now, yes, of course, what I'm describing here does assume constant acceleration. We can't have completely wild motion. I mean, the concept still applies. It's just, anyway. Okay, but anyway, the limiting case is when delta t goes to 0. What is ultimately that slope that's being approximated here? And then we go and say, okay, we can characterize what the speed is right at that moment in time. It's basically what a speedometer tells you, right? If you're accelerating, it's hard to characterize what your speed is in any, overall until you just start to say, okay, well, like 1 second I'm going this fast, and then 2 seconds I'm going this fast. That's what we're looking to do. Okay, so that's how we're going to start to look at these graphs here. That the slope of the position time graphs are going to yield speeds. If we have curved position time graphs, then we take the instantaneous speed definition and we look at the limit that t goes to 0. But right now, we're still doing things very qualitatively. Okay, still very qualitative. Let's do some examples though, so you can really see how this works. Oh my gosh, look at this problem. This is amazing. Okay. We got a train car, moves along a straight track. The graph shows the position as a function of the train. What's happening here? So read over this and put a letter in the chat. Now, I know I don't have letters here, but bingo bango. I don't know what option is bingo. I'm not sure the bingo bango option. A lot of C's. Bada bing. I don't know what option. Bada bing, bada boom. People are confusing me. All right, what's happening here? You're looking at the slopes. Let's see that. Let's look here. The answer here. Do I have it highlighted? I don't have it highlighted. Oh, sorry. The answer here is. Let me circle it. My thing here. We're slowing down. Number 2. The answer is 2 or B. B or 2. But 2 or B. But B is 2. Yep. Why? Let's look at it. The position is constantly changing, right? The rate is changing as well. And so we want to draw little tangent lines. Let me do that right now in red. So right at the start, that's not a line. It's still a circle. Where's the button for the line? Somewhere. Okay, here we go. There is. Oh, that's terrible. Oh, so annoying. All right, here we go. That's our slope when we start off. Now, what about around here? Where is the slope? Slope is like that. Then we get up here, the slope looks more like this. So you see, as we progress through here, right, we're getting a line, getting a slope that's getting less and less steep. That means the speed is going down. And you can make sense of this too when you look at the graph. And what it's saying here is that your change of position over time is dropping, right? In a given interval of time, at the start, we traveled a lot of position, but then we get up here, we're only moving, a little bit of position. So that's 2. That's 2. So the slope's a little harder to visualize here, but you kind of you can kind of imagine throwing in the slopes every few seconds, right? Maybe right there, right here. There's one here, there's one here. And you can see how the slopes are changing. And that tells you what the speed's doing. It's going down. All right. Questions about this one? Anything unclear about this?
Can you represent what 3 would be next to that graph?
Oh, yeah, sure. It would be, well, it would look something like this. Let me try to crudely draw this. If you make fun of me, I will absolutely kick you out of Zoom. So, although it's fine. I draw like a kindergartner, so. Speeds up part of the time. That looks like it's going to be like this. And then maybe it does that. That'd work. Because, actually, that doesn't work at all. How about this? Doesn't work. That's actually more than what you asked for. Probably, let me draw this line instead. So something like, that was right, what I had before. Yeah, no, sorry. What I had before was correct. So this would be slowing down, and then we're kind of speeding up here. So this first part's speeding up, right? And then right here in the middle is where we have the fastest. Let me draw that a little more accurately. It looks a little dumb. Although I think literally my next example is this, what I'm doing right here. Okay, so this is what happens here is we actually are speeding up during this section. This is top speed right here, right around here. And then we slow down. So that's what would be 3. Speed up all the time would just look like that. That'd be speeding up the whole time. Constant velocity, right? It's just a straight line. That's not that straight, but so okay. Anyway, I think literally my next example is what you asked me, so I should have just shut my mouth and kept going. Oh my gosh, here we go. Should have shut my mouth. All right, so we want to interpret this. We want to find the velocity from the position time graph here. So let's first look at what's going on here. Let's describe it before you do anything. I'm not even looking at the questions right now. I'm just trying to understand the motion. We start at a negative position, moving at some speed to the left. We slow down gradually until we reach position A, where we have apparently come to a stop. Just instantaneously stopped, though, because the slope at point A is 0. And then we start to speed up from point A, right? We start to speed up. We're going a little faster, until we get to B. We're going the fastest through B. Once we pass B, we start to slow down a bit, and at some point before we hit the C, we've come to a stop. That's what's happening in this motion here. All right, this is an elevator, apparently. At which labeled point or points does the elevator have the least speed? Well, A and C, if you say 0, right? At what point or points does the elevator have the maximum velocity? That's B, because at B is the steepest slope. And let's look at what the graph looks like. So here's the velocity versus time graph for this position graph. Now notice at the locations A, B, and C, well, at least at A and B, C is the same, would be the same as A. So let me draw that in there actually. But they show the slopes, so we get a sense of what the speed is like. Let's do a soft blue. Here. And I want a line zoom. So it looks sort of like that. So it's very similar to A. So what's happening here? Well, we start off with a negative velocity, right? Because the slope, right when we start, looks like this. Slope, right when we start, looks like that. So that's a negative velocity. So we start off negative. By the time we reach A, we've come to a stop. So the velocity starts negative, and it decreases. When we get to A, we've come to a stop. So it's 0. But notice what happens at A. We turn around. It's a turning point, we call this. And then we start to increase in speed. So here we go. We cross the origin here. It means we've changed direction. When you cross the origin in the velocity time graph, you've turned around. So now we're positive. We're moving towards B. B is the biggest speed. Now something dramatic happened at B apparently. You can't notice that too much in the position versus time graph. This is what's known as an inflection point. It's got an interest in second derivative. Don't worry about that for now. But at B, yeah, something happened and we just completely changed how we're going. Our acceleration just instantly changed. And now we're slowing down. At some point we come to a stop and then later C occurs. Now, this is a slide that should leave you a little puzzled. This should be a little uncomfortable. This should make your brain hurt a little. And I would definitely recommend you spend a little bit of time later going back through this and understanding the relationship between these two graphs. I mean, I'll simply say this. The bottom graph is the derivative of the top graph. That's it. But that's the mathematical side of it. And that's all it is mathematically. Mathematically, it's just like the bottom graph is the derivative of the top graph. But in terms of the meaning, the context, be able to describe the motion, what's changing, what are they doing, there's a lot of information in here. And what's challenging is the mathematics are not so bad. The challenge is taking that mathematics and turn that into the physics. Meaning, are we explaining the motion properly? Are we displaying things? If I just threw these graphs at you, could you tell me a story that would be accurate? I don't know about the bottom being more curvy. I think it's okay. I mean, this is supposed to be a parabola from the origin to B. And then B is partially a parabola until you reach, it's a little complicated if you actually want to model them with functions or something. Yeah, okay. So
I did have a question on the velocity graph.
Yes.
Isn't initially the velocity decreasing?
Yes, it is.
That it's growing larger in the negative direction. So wouldn't that be
No, it's not
before
growing.
A?
No. It's not growing larger in the negative direction. We're slowing down. We have a negative value. Say it's like, I don't know, negative 20 meters per second, and that's going down to 0.
Oh, okay.
And that's what's being here. Yeah. Yeah.
Thank you.
Yeah. When I mean a tangent line, and again, for a lot of you may be in 150 and you're about to see this stuff, but when I mean tangent line, these lines that are drawn here are what's known as the tangent lines. It's a line that you can draw that touches a curve at one point, right? So this curve down here, is there a way to draw a line where it touches at literally only one point? And that is right at the edge there, right? Same thing with B. We're only touching the graph right at one point, and it's if the graph were to continue in a linear fashion, what would the direction be? That's what it's saying there. So if we zoom in a ton to this and look at the little tiny delta t's, the graph's going to look like that straight line. Okay, so that's what I mean by that. Okay, so I got a bunch of yes.
Could you make a tangent line at C?
Yeah, it look just like the one at A.
Okay.
Completely flat. It'd just be like that, totally flat.
Oh,
it runs by the graph and it touches just at one point and it approximates what the slope is at that point.
so is it just a random line, or is it just like it's specifically only touching the curve?
It touches the curve. It doesn't cross it necessarily. I mean, they're showing it cross here at B, but it doesn't have to cross. The idea is that you want to touch the graph, but not necessarily cross the graph.
Oh, okay.
Yeah. So like at A, I don't really cross the graph, just touch it right at A. This one touches right at B. They show it go through. It doesn't have to go through, but yeah.
Professor?
Yeah.
Does the graph for A represent the position function, or like the position function of that thing? Okay.
Yes, this is the position versus time graph, and the one on the bottom is the velocity versus time graph. Yes. Oh, it sounds like you guys are gonna love the homework because you're going to have to do this a lot. You're gonna practice it. Oh man, learning is You guys are going to be learning stuff. I'm just so excited for you. When I took this class, I was lost. Man, I had no idea what the hell I was doing. So if you feel like you don't know what the hell's going on right now, I would say that's normal.
Professor, is C still considered a turning point? You said that A is a turning point.
A is
C
a turning point. C is not a turning point because at no point do we... It looks like we're kind of at rest for a while through C.
Okay, thank you.
Turning point... now, so let me say a lot about turning point here because I'm going to say more about turning points a little bit later. But turning points are always this. They represent local minimums and maximums on position graphs, if you know what that means. And they cross. They cross the time axis in a velocity graph. So notice how A crosses the time graph, but C does not. There's the difference. Okay. It's going to be a fun journey this semester. Learning physics. Okay. Any more? I love the questions. B is an inflection point. You bet. You bet. Something interesting happens at B. What happens at B is the acceleration changed. Yes, it changed. So the second derivative is a little wonky. All right. Boy, these questions are good. Love them. You know why? Because here's why. Let me show you this real fast. Something I learned. I can make a graph for you. Check this out. There's a graph. This graph is, on the vertical axis is the number of questions you ask me. Right? Oh no, the bottom is the number of questions you ask me, and the vertical axis is the number of questions is how hard the material is. So what happens is there's not a lot of questions, the material is very easy. And then the material gets harder and I get more questions. And I get more questions and I get more questions. And at some point, it does that. And at some point, it gets so hard that I don't get any questions. And as a teacher, I want to be right here. Sometimes I'm down here or I'm down here. I have no idea. So I think we're over here. And it makes me very happy. So that's great. Okay. What's the slope of this line? I have no idea. What does that mean? Okay.
It's a slope.
It's a slope, but what does it mean? The rate at which it's difficulty versus questions. It's a D difficulty over D. I don't know. Let's just keep getting. I gotta get this done on time. I'm ranting too much. I need to shut up. Okay. I gotta stop. I gotta shut up. Okay. Here we go. Question for you. Here's the motion diagram of a car moving along a straight road. What's the correct position versus time graph? Do I like D? I love D. Okay, why the other one's wrong? A says we start at the origin. We do not. C says we start at the origin. We do not. B. Well, what's the difference between B and D? The speeds are different. B is telling us that we're moving faster to begin with and slower later. Where D has that reversed. Slower at first, faster later. And that's what's happening here. We're slower at first and faster later. Excellent. Keep going. Here's a motion diagram of a car moving along a straight road. It's the same one. But now I would like you to tell me which one is the velocity versus time graph. Which one's the velocity versus time graph? Before you do that letter, think an extra couple seconds. Think a little bit extra. Take 2 more seconds to think of this. A lot of C's rolled in at first. Then we started wavering around A and D. All right. Uh-oh. The answer is C. It's C.
What?
Well, what's going on here? For the first 3, I don't know, say this is 3 seconds. What is this? This is constant motion, right? What about this? This is constant motion too. These are constant speeds. What is A, B, and D telling me? A, B, and D are telling me at some point in the motion, I am increasing my speed gradually. Oh, that's not happening here. I'm not doing any of that. C is right. C shows a flat graph showing constant speed. Then we got this little jump here. We just instantly change to a higher speed. And that's what C is doing. E is just apathy, which, fine.
I have a question.
Yes.
So, does the 0 mean anything for this? Because it's like it
No.
starts before 0.
Nope. It does not mean a thing in this graph. Nope.
Okay.
But it does mean something because one of the things we're going to learn, I don't think we're doing it today. If we do it, we're barely going to touch on it today, but you can go backwards with these. So right now we're working on taking position graphs and try to create velocity graphs. You can go all the other way. You can take a velocity graph and create a position graph, but you need to take an integral and you need to have an initial condition. So the 0 doesn't matter for this graph, but it does matter in the position graph. Right? So
I have a question.
yes.
Technically, if we're talking realistically, technically, isn't C impossible as well?
Yes, it is impossible, right?
Okay.
But we're not that's not what we're doing. We're creating models here. We're trying to explain things and we make a lot of simplifications. Yes, this is an average here, right? We don't know what happened at the origin. Something dramatic happened. I mean, we probably just for like a tenth of a second just started sprinting and it's just like this really, but we don't care about that detail. Now, normally I would say though, is what I normally do is when I have a vertical line like this, I like to make it dashed. And I forgot to do that for this one, but you'll see all my future ones, they have a dashed line to indicate like a discontinuity that we just instantly change, which is fine. Again, we're not trying to perfect our explanations here. We're just trying to develop the thing. I mean, in a way, yeah, you could say that you teleport or something, we just.
So it's C because it's constant?
C is the only graph that shows constant speeds. All the other graphs are showing steadily increasing speeds, which means acceleration. We're not accelerating here. You see that? There's no acceleration here. It's just a constant speed. Magic happens at some point, and then we're going faster. So, yep. Okay, cool.
Okay, thank you.
Yeah. All right. Anything else? Okay. What about this one? A lot of questions. I said, this is a position versus time graph. What's the velocity versus time graph? Again, sometimes it's helpful to rule out the wrong ones because it may be easier to understand why something is wrong than why something's right. You can quote me on that. That's a quote. I just made that up. That's a pretty profound statement. All right. I'm loving the C's I see rolling in here. It is C. I think you learned something because you got this one wrong and then you got this one right. And that generally means you learned. I'm so happy that you're learning now. Okay, cool. Maybe you got both right. Maybe you got both right. Maybe you got both wrong. Oh, well, the learning's coming later, I guess. But. All right, what's happening here? Well, A and B are wrong, right? They're showing, A, we turned around in A. That's not right. B, we're speeding up. No. We do have a constant speed here. It's a little bit hard to tell, but this is straight initially. This is straight. And then it starts to curve, but that curve means we're slowing down. And only C is telling us that. Positive speed, then we gradually slow down. Now D almost looks good, but D is saying constant negative speed, and then we slow down. Okay, that would be if the graph was like flipped the other way or something. It's just we have initially a positive speed. Okay, well you'd have to have a negative slope. That's what I mean. So the graph would flip like vertically or something. So, oh gosh, what would A look like? A would start off with a parabola to start, it would actually look a lot like, so A would look a lot like, let's go back. I mean, like, look at A. Look at this right here, right? That stuff is the same as this, so it's a parabola right here. That's what A would look like. At least initially, looks like that. So, but if A was right, you'd have to have some kind of behavior like that going on. So, yeah. Okay, man, you guys are inquisitive. I'm very sad that we don't see each other in class, because, in fact, this material, I covered this material, and then we went into lockdown mode. I think the last lecture I did was probably like, it was kinematics, I guess. It's bringing back memories. Oh my gosh, these questions are amazing. All right, next question. We got two objects, and I'm showing you their position versus time graphs. So, at what point do they have the same velocity? Oh, how far am I here? Oh my goodness. Oh my gosh, I got alphabet soup going on here. I don't like alphabet soup, it's disgusting. All right, we're settling in on B maybe. But I don't like B. I don't like B very much. I really don't like B. No. Remember, how do you determine speed from a position versus time graph? Somebody tell me, how do you determine speed or velocity on a position versus time graph?
Slope.
Slope. So you're looking at slopes. The answer's not B. B's got something interesting. That is the location where they meet, but they do not have the same speed, because one is going way slower at that point, right?
You have to match tangent lines.
Ooh, I love that. Oh, I got tickled all back of my neck. Oh my gosh, I didn't expect to get that excited from that response. That's a good response because it's right. And let me show you it. Here's the tangent line for one, right there. And that matches to, we're at that location. That location is somewhere around here. So what is one doing? One is really going fast. One's faster at first, right? And then at some point it slows down, it matches to, and it continues to slow down. And then when they meet, two is going to pass one. So that's what we're seeing at T0 here, is two is overtaken one. One was initially faster, then it started going slower. But before T0, which the answer is A then, oh, come on, Zoom, cooperate. But the same slope, oh, well, they already drew that there, I guess. Sorry. But yeah, so same slopes. A. If your brain hurts, I'm very sorry, but trust me, it's like exercise, and it hurts now, it'll feel better later. It will. All right, let me do this one. There's a lot going on here. Now how much time do I got left here? Oh brother, I got 8 minutes. Hold on, give me time to assess the situation. Give me time to assess the situation here. We got. Oh, I'm fine. I won't get through everything now, but that's fine. I only like maybe an extra 10 minutes, and I'll just do that in lab. So we'll just.
So if this is like exercise for your brain, then if we pull a brain muscle, then do we have to take time off to let it recover?
No, you push through the pain. You just gotta push through the pain, man.
All right.
Yes, physics waits for no one here. That's called a stroke. All right. Okay, let's go through these examples. These are fantastic. In fact, let's see, what's the next slide? Okay, I'm going to stop after this slide, and the rest of the stuff I'm going to talk about in lab. But let me just finish this last slide up here. All right. So the figure shows a position versus time graph for a moving object. That's great. Okay, so now, again, before I read these questions, I want to look at the diagram and I want to try to understand for myself what is happening here before I even think about questions. In fact, I have this on a slide, so let me bring this up actually. Okay. So, well, initially we just kind of hang out somewhere. That's point A. We just not moving at all. And then at some point we decide to move to the right at a constant speed for a while. We cross the origin, and we get to location C, and again we just kind of hang out for a while. And then we decide to walk back towards the origin, so we change direction. Looks like that is a steeper slope, by the way, at D. So we're probably moving a little faster. And then when we get to E, we are just relaxing again. So, at what point is the object moving the slowest? Now, I have interpreted that to mean non-zero velocity. Okay, if you want to say that a zero velocity is the slowest, I can understand that. And if you said ACE, I wouldn't have a problem with that. I'm saying B because I'm going to consider, what's the slowest non-moving? Because they just say, is the object moving the slowest? Well, okay, so it's kind of semantics, but whatever. I'm saying it's B. D is faster. Right? Object at rest, well, that kind of qualifies A as meaning, what it means. But anyway, objects at rest at AC. Does the object have a constant non-zero velocity? Yes. Both during B and D, the speed is constant. And then D is a negative slope, so we move to the left for D. Okay, so any questions about those letters for that first example? All right, let's go to the next example then. Okay, let's read the graph first. What's happening here? We are moving fast to the right. We are starting to slow down though. We reach B, where we have instantaneously come to a stop. Instantaneously, because we immediately changed direction, and now we're heading back towards the origin. We're speeding up as we pass through C. When we cross the origin, just by coincidence, when we cross the origin, we're moving the fastest. And then we start to slow down again as we continue to move to the left. And then at some point we come to a stop. Now let's go through the questions. Is the object moving the fastest? Where? Well, it's at D. D has the steepest slope. Is the object moving to the left? That would be a negative slope, indicate a negative velocity. That happens at C, D, and E. They're all negative slopes. Is the object speeding up? Yes. At C, the object speeds up. In fact, between B and D, we can say the object speeds up. Between the origin and B, where A is, we are slowing down. And then from D down to where we come to a stop around F, we are also slowing down. The object turns around at B. We change direction at B. Local maximum right here. So last time we had talked about position graphs, how to interpret them, and we found that the slope of position graphs will give you velocity. And so we worked a little on developing velocity graphs, and we're going to continue that a little today, and then we're going to get into acceleration graphs. Now, we did develop an equation last time, real simple equation that only applies under uniform motion, meaning no acceleration. And that's the equation that you see right here. Now, there is another way that you can write this equation. If you move the S sub I over to the other side of the equation, you can just create a delta S. And you have a same equation, but the delta S would mean displacement, and that would be equal to the velocity times the period of time. That's the definition of velocity. I mean, that's really what this equation is, ultimately. It's just the definition of velocity, just written a little differently. So, that being said, if we have, velocity information in time, in principle, we should be able to work backwards and determine what a position graph would look like based on information about velocity. So we're going to do that. That's the next step here. Now, if you've had a little calculus, if you're familiar with a little calculus, you probably have an idea where this is going. If we try to go backwards in going from a velocity graph to a position graph, that's going to be doing sort of the opposite mathematical operation there, which is an integral. Okay, so I do realize a lot of you are probably in 150. You have not got to integrals, so I'm not going to attempt to ask you to perform any integrations at the moment. But I will explain to you, at least from a graphical standpoint, how you understand that. Okay, so let me jump ahead here to this picture. Now in this picture, we have a very strange looking velocity graph. This is not a standard velocity graph we work with. This is just drawn here for the purposes of the mathematical explanation. And what you can do is this. Imagine taking this graph and form a little triangle under it. The triangle, not triangle, rectangle. I know my shapes. All right, try to form a rectangle underneath the curve there. And the rectangle is going to have dimensions. Delta t, which is the base. That's a small interval of time. And the height of this rectangle is the average speed. And if you calculate the area of this, it's going to be velocity times delta t. Well, that's what displacement is, right? So if we work out these small little areas bounded by the graph, we're working out basically tiny displacements that are occurring. So then we could just add up these rectangles from start to finish, and the total amount of area that we determine, right, is going to be the overall displacement. Now you see the rectangles I drew here, though, they don't perfectly approximate what's going on with the velocity, but that's where the calculus comes in. You take the limit that delta t goes to 0, right? And then your areas become closer and closer to what they actually are. And in mathematics, this whole idea of doing that is what's known as the integral. And so we can write it this way. This is the symbol for the integration, but we're not going to perform any integrations in the sort of traditional sense. We are simply going to understand this as trying to work out what the area is under the velocity curve. And that's sort of the point of this. So when we work out problems here to try to figure out positions, we're just trying to work out areas. We're not trying to do anything that's too mathematical, I'll say. All right, so here is a question for you. Here is the velocity graph of an object that is at the origin. So x equals 0, t equals 0. At 4 seconds, the object's position is what? So just to remind you, what you're going to do here is you're trying to determine the area bounded by the velocity graph. Now, these are the kind of velocity graphs we work with. Nothing too crazy, either constant speed or a gradual speeding up or slowing down. And I actually have the coordinate system drawn here with grids so you can more easily work out areas. But you want to try to work out what the area under here is. So what do you think the letter, what does that correspond to? A lot of C's. I like it. This is right. Now, one very subtle detail here that you need to be aware of. Technically speaking, if you're working areas under the curve here, you're working out displacement. What we know is that wherever we were originally, we have moved 12 meters to the right. That's what we're saying here. But we also happen to know the position as well because we are told what the initial position was. The initial position was at 0 meters. So if our displacement is positive 12, then we simply move to a position of 12 meters. Okay, there is a small difference. Displacement and position are slightly different things there. So with that being said, what do you think about this question? There's another one. Same exact problem, but now the object is going to start at a position of x equals 4 meters. So then, where would the object end up at the end of 4 seconds? All right, B is good because B is right. The displacement's still 12 meters, but we start at a different location. So the final position ends up being 16 meters, 4 plus the 12. Okay? All right. So,
Professor,
now, yes.
can I ask, how did you get displacement 12? I still don't understand that.
So here's what we're doing. You're working out the area bounded by this graph. And so you can break up this area into these squares. And it looks like each square is an area of 2. This is 2. Right? This is 2. All the boxes are 2. Oh, kindergarten 2s. 2, 1, and all that together is 12. So that's what we're doing in these problems, is just adding up these areas here. In fact, you can see more of the development of this. I mean, after the first second, we've moved 4 meters. And then the next second passes, and we move another 4 meters. But then we start to slow down. So the next second's only 3 meters. The last second is just 1 meter. So you actually, that's how you would create your position graph, actually. You'd start at 4 meters, 0 seconds. And you kind of, you know, with these intervals, just each interval, just work out what the position is, or sorry, the displacement, and then you go from there.
Oh, okay. Thank you.
Yes. Okay. Fantastic. Any other questions before we move on? So I'm actually going to do that. That's my example here. So let me bring up.
So
Yes.
I got a quick question. So if that's how you calculate the displacement, then how did you get 16 this time?
Because what we do is ultimately the formula is this thing you see at the bottom here. It's the area under the velocity curve. That is technically what the displacement is. And you add that to your initial position to get your final position. That's ultimately what's happening here. So I got 16 because this graph tells us that we moved 12 to the right. But from where? Well, we moved from 4 over 12, and that's why we get the 16 here. So when you're going to figure out positions from velocity graphs, you got to be mindful of the initial condition, 4 meters. And again, if some of you have had integral calculus, what this is the plus c that shows up when you do integration. So anyway, not something you need to know, but just if you happen to know it. All right, so let's do a problem. So I'm going to zoom in a bit here. We are given a velocity graph, which you see on the left-hand side here. And we're told that we're going to start at an initial position of 10 meters at 0 seconds. And we want to figure out what the position time graph is going to look like. And then answer a couple questions about the motion. So let's do it. Now, this is done in sort of a similar fashion as the other one. You can work out, what I like to do here is, I have a grid on my coordinate system here, and so I can say each square represents a certain area, right? And it turns out with 2-second intervals here, each box is going to represent 10 meters. So 10 meters, 10 meters, all the triangles would be 5 meters and so on. If we are below the time axis, that would be considered a negative area because your velocities are negative. So down here, these are all negative. So what I want to do when I want to draw this out, I have my time coordinate system down here. I have my position coordinate system, on my axes here. And I'm going to start at 10 meters, 0 seconds. That's where I'm told that we're going to start. I'm going to draw little dots here that kind of go along with what we're doing. So that's my first dot, and that's something I was just told in the problem. 10 meters, 0 seconds. What happens in the first 2 seconds? In the first 2 seconds, we have traveled an additional 20 meters. So now we're at 30. We start from 10, go to 30. And that's at 2 seconds. What happens over the next 2 seconds? Well, the area here is 15. So now we're going to go forward an additional 15 meters. Now we're at 45. And that's right there. The very last part here, the last 2 seconds of this forward motion here is 5 meters. So we went from 45 now to 50. And then what happens here, when you look at the velocity graph, we cross the time axis. So we go from positive to negative velocities, which means we've turned around. That's our turning point at 6 seconds. We've changed direction, and now we're heading back to the left. And the past 6 is completely symmetric to what happened before 6. So the areas are the same but negative, and so we can just put the same points down that we had before. And that creates our position time graph. Now the first 2 seconds and the last 2 seconds are technically straight lines because it is constant speed, but during from 2 to 10 seconds, that's parabolic. Okay, that's just the nature of the mathematics there.